Alright, so today we're looking at section 4 from chapter 5, day 2, which is domain and solving of logarithmic functions. Alright, so let's first take a look at how to find the domain of a logarithmic function. So if we're taking a look at a logarithmic function, this is saying that the argument of a log as well as the base of a log have to be positive. So if we have like a log base, let's just call it log base b of a for base and argument. Log base b of a. If we have this, then that's telling us that a has to be positive, right? The argument must be positive, and b has to be positive. So we can't have anything like this. So if we had something like log base 3 of negative 7, that wouldn't work, right? Because we have a negative in our argument. Or we couldn't also have something like log base negative 2 of 9. This wouldn't work either because we have a negative in our base. So we're told that we can't have a negative in the argument and we can't have a negative in the base in order for us to be able to evaluate a logarithm. So let's take a look at an example of finding the domain. Alright, so for this problem we're trying to find the domain of our given function g of x. So g of x is equal to the natural log of the quantity x minus 1. We can rewrite this as a log with a base, right? So we can say g of x equals log, and then the base for natural log is e, so log base e of the quantity x minus 1. Now, when we're looking at this, we know that we need two things to be positive. We need our base to be positive, and we need the argument to be positive. Our base is already positive because e is about 2.72. which is positive, so we don't have to worry about the base. So the main thing we need to focus on is the argument. So what values of x make our argument positive? That's what we're trying to figure out right now. So we say x minus 1 has to be positive. So to figure out the values of x, just add 1, right? And we then would get that x has to be greater than 1. So if you pick any value of x that's greater than 1, that will make our argument positive. Any value less than less than 1, if you plug that into our argument, that's going to give us something that's negative. Now, if x equals 1, when we plug 1 in, 1 minus 1 is going to be 0, and 0 is not in the domain of a logarithm. So we don't want it to be 0, we want our argument to be positive. So if we're looking at the domain then, the domain is the set of all x such that x is greater than 1. Now we're also probably going to want to talk about this in interval notation, so it's going to be all values of x from 1 to infinity. Again, we're using the parentheses here because it is not including the 1. So this right here and here, those would be our solutions. That's our domain. Alright, so let's take a look at a little bit more complex example and trying to find the domain of this logarithm. Of this logarithmic function. So we have a logarithmic function with a rational argument. So we have this note here. It says when finding the domain of a log with a rational argument, there are two things that we have to look at. First, our denominator can't be 0. And second, just like with a normal logarithm, our argument still has to be positive. So once we figure out values that make our denominator 0, so values that are undefined, and then values that would make this equal to 0, we're going to then have to check left and right intervals on the number line to see what makes whether in that interval our logarithm is positive or negative. Okay, so let's take a look. First, let's look at what makes this denominator 0. So remember to figure that out. To find the domain restrictions on this, we would just say whatever the denominator is, set it equal to 0, and we get that x cannot equal 0. Pretty straightforward for this one, right? Just take the denominator value and set it equal to 0. So that's the first restriction that we're going to have here. The second one we're going to look at is what actually makes this whole thing equal to 0. Because remember, we don't want our argument to equal 0, we need it to be positive. So what makes x plus 1 divided by x 0? What makes it 0? So in order to do this, the first thing that I'm going to do is I'm going to multiply both sides by x so that we can get rid of this in the denominator and we'll just have a nice function to deal with. So we have x plus 1 equals 0. We can then subtract 1 from both sides, and we get that x equals negative 1. So we have two values that we're looking at here. We have x equals 0, and we have x equals negative 1. So now we're going to plot these on a number line, and we're going to take a look at values in between them and outside them on intervals to determine whether those intervals are positive or negative. So let's make a number line here. Have a number line. Let's make it a little thicker so we can see it better. And then let's check intervals. Okay, so I'm going to put the 2 points on our number line here. Here we have negative 1. Here we have 0. And we're going to check values on the left of negative 1 to the right of 0 and numbers in between negative 1 and 0 and determine whether on those intervals our argument is positive or negative. Okay, so let's pick a number that is less than negative 1 so we can check this interval. Maybe negative 2. So let's try negative 2. If we plug negative 2 into the argument, what do we get? Let's do this in a different color. Let's do this in green. So we have negative 2 plus 1 all over negative 2. That's going to be a negative divided by a negative, which is positive. So that means that this interval, every value to the left of negative 1 is positive. Let's check a value to the right of 0. Let's say maybe positive 1. So we have 1 plus 1 over 1. That's going to be a positive value over positive value, which is positive. So we have another positive here. And then let's pick a number that's in between negative 1 and 0. Maybe negative 1/2. Negative 1/2 plus 1 all over negative 1/2. This on the numerator is going to be a positive 1/2, so it's a positive number. The denominator is negative, so a positive divided by a negative is a negative number. So we have a negative here. So that means we have two intervals that work. We have all the values to the left here and all the values to the right here, the two positive intervals. So we need to figure out a way to write this so that we can talk about our domain. Remember, we can't equal negative 1, this is negative 1, and we can't equal 0, so we're going to use parentheses, and it's going to be all values to the left of negative 1 and all values to the right of 0. So if we're talking about the domain here, right, the domain, it's going to be the set of all x such that x is less than negative 1 or x is greater than 0. Now what would this look like in interval notation? Well, for this is saying we're going all the way off to negative infinity, so we're going from negative infinity, and we stop right here at negative 1 to negative 1. And then all these values in between negative 1 and 0 don't work. We start up again at 0, and this goes all the way off to positive infinity. So these two here would be our domain. So this here and this here would be the domain. Alright, so for this problem, we're no longer looking at trying to find the domain of a logarithmic function. We want to try and solve it. We want to figure out what value of x makes log base 3 of the quantity 4x minus 7 equal to 2. We want to know what value of x makes this true. Now, in order to do this, we need to get the x out of our argument. We need to remove the x from the argument of our log. And the only way that I can really think of doing that is to change its form. So remember, we know how to change back and forth between logarithmic form and exponential form. So that's what we're going to do. We're going to change to exponential form. So we're going to change this into exponential form. So remember, we talked about this yesterday. If you have the base of your log is just the same as the base of your exponential, so 3 is now the base of our exponential. And remember that this whole thing, the whole log, is actually just the value of the exponent of our exponential. So this is equal to 2. So the exponential is 2, right? The exponent of our exponential is 2. So 3 to the second is equal to our argument, 4x minus 7. So we have this here. 3 squared equals 4x minus 7. So now, just solve. So 3 squared is 9. 9 equals 4x minus 7. Add 7, we get that 16 is equal to 4x. divide by 4, and we get that 4 is equal to x. Now, we think that this is probably our solution, but we have to double check and make sure. We have to see, is this in the domain of our logarithm? So let's just do a quick check here to make sure that all is good. So we'll take 4, we'll plug it back into the argument and make sure that our argument is positive. So 4 times 4 minus 7, is that going to be positive? That's 16 minus 7. 16 minus 7 is 9, which is greater than 0. So it all works out. We are good. So x is 4. Alright, so again for this problem we're trying to solve for the value of x that makes this true. So now x is no longer in the argument, it's in the base of our log. So last time we looked at what did we do if we had x in the argument. Now we need to get x out of the base. Again, in order to solve this, we're going to have to change it into exponential form. So change to exponential form. So remember, we said before that the base of our log is the same as the base of our exponential. So it's x. And then the whole log is equal to the value of the exponent. So it's x squared equals our argument, which is 64. So we've actually seen this a lot. We know how to solve these. It's set up very nicely for us to solve right now. And let's use square roots. So we can take the square root of both sides. Remember, anytime you introduce a square root, you have to take the positive and negative square root of both sides. So we get that x equals plus or minus 8. Now, x is plus or minus 8. If we take this and we take a look at plugging it back into our log, we have to do a quick check here. Now, what did we say was true about the argument and the base of our exponential function? We know that the argument has to be positive, but so does the base, right? So because the base has to be positive, right? X has to be positive, we know that x cannot equal negative 8. So that means that the only solution to this is x equals positive 8. So positive 8 is going to be the only solution that works for this logarithm. Alright, so for our last example, we're given an exponential function. So it's no longer, we're not given a logarithmic function, we're given an exponential function. So we have our variable and our exponent, and we need to try and solve this. Now, we talked about solving these before where they had the same base. Unfortunately, these don't have the same base. So in order to solve them, we're going to have to change this into logarithmic form. So we're going to change to logarithmic form. So we need to change this into logarithmic form. So let's do that. So remember, we said that the base of our exponential is the same as the base of our log. So this is log base e. And we know that the exponent is just what our log is equal to. And then the argument is this here. So this is log base e of 5 equals 2x. Now, there's a nicer way to write this, right? A log with base e. We call this natural log. So we're going to use the natural log. So we're going to use natural log. So this we can rewrite as the natural log of 5 equals 2x. So now we need to try and isolate the x here. So this is just some constant. It doesn't look like it. It looks like there's some variables in here, but these are just a function. So this is really just some number. So we can take this number and divide it by 2. So let's divide both sides by 2. And we get that x is equal to the natural log of 5 divided by 2. The natural log of 5 divided by 2. So this is the solution to this exponential function.